general solution of binary bits problem. We made a guess in a previous video, and in this one, we need to prove it. So you can expect in this video, we need to do a lot of math work. Relatively complicated, but I hope you can understand. Yeah. So I tried to go through all the details, but you need a lot of math knowledge to understand, especially about logarithm. You need to familiar with the basic properties of logarithm. Yeah. All right, so let's start. Our problem 10, and we guess the formula. Yeah. The strategy here we use guess and verify approach. Yeah. So we made the guess based on a special case. N is power of 2. So here you can see another reason we want to look at a simpler special case, because we use that as the clue for us. We use that, the result for a special case, to give us some clue to make a guess for the general case. Now, here we use that. So you can see that special case is pretty valuable. Think about, without this special case, how can you make this guess, right? How many of us can make this guess? Very hard. Yeah. All right. The next thing is verify it, prove it. How to prove it? Here we have a goal. We have this. This is our goal. We need to prove mathematical induction. Mathematical induction. Yeah. So you can see this tool is extremely powerful. So we use it another time. Yeah. In this class, we use mathematical induction several times. Yeah. All right. The base case verification, that's easy, right? Yeah. So n equals 1. Yeah. So that's the answer, right? Induction assumption. We make induction assumption. We assume A of k equals this format. For what kind of k? You need to specify the range of the k between 1 and n. Any number, if it is between 1 and n inclusive, we can apply this formula. That's the meaning of this induction assumption. Yeah. If you want to look at the mathematical induction type 2, we have two different types, right? Type 1, type 2. Type 1 is not like this, okay? But type 2, here we need to use the type 2. Yeah. The two types are equivalent, yeah. But type 2 is more powerful than type 1. Yeah. So here we need a more powerful version, type 2. Yeah. All right, the last step in mathematical induction, when k equals n plus 1, we need to show it. Okay? So we need to do the work here. You need to do a lot of work to show it is true. It is true. All right, if you can show it is true, then we have the conclusion. For the general case, we have this formula. That's all we need to do. Yeah. All right, so let's start the proof. Yeah. We look at n is odd and even, two different cases, because the formulations will be different. Yeah. So for n is odd, we can write it as n equals 2s minus 1. Yeah. Here I use s, but do not connect to in our original representation, that s. Yeah. Here, I just want to use a different variable. Yeah. It's not that, previous s, the meaning, the subscript s. Here just some ordinary variable s. All right. Now we do the formula transformation. All right. We assume s greater or equal to 1. Then let's change the form of a of m plus 1. Using that form, plus 1, so you get 2s. That's even number. So that's the reason we start with n is an odd number, right? Because not odd number, after you add 1, you get even. So we like the even number in this parenthesis here. Okay? Then based on our recurrence relation, you will get a of s plus 1. Divided by 2, 2s divided by 2, that's s. No remainder, so a of s plus 1. So that's the first transformation we have. All right, then we can apply mathematical induction on a of s. Can we apply mathematical induction on a of s? We only need to check, is s in this range? S? Yes, we're pretty sure s in that range, right? Because s equals n plus 1 over 2, definitely less than n. And the greater equal to 1, so we have that. So s falls in that specific range for the induction assumption. So we have this expression. 1 plus 1, so 1 here plus the 1 there, 1 plus 1, so we have this 2. All right, so that is the one side, left-hand side expression. How about right-hand side expression? We need to work on the right-hand side expression and see if they are the same, right? So here it's pretty messy. Let me make it, look a little better. Pretty messy. All right. Then let's work on the right-hand side and see if they are equal or not. That's what we want to do. All right. To do that, we need help from a special formula in our textbook. Here, we need to use a special formula. So what's that formula? Let me show you. First, 1 plus floor function of log base 2 of 2s. Okay, 2s, 2 times s, right? Here we need the logarithm property. Do you have idea? The logarithm property, log base a xy equals x plus. So we need to use this property. 2 times s, right, equals log base 2 of 2, that's 1. Log base 2 of 2, so then log base 2 of s. So, all right, that property. Then this one inside floor function can be pulled out of the floor function. So we need that formula. So that is this formula. When you have an n inside a floor function, we can pull it out of it. Any integer n, we can pull out of it. So that is given in our textbook page 477, Appendix A. It's a simple, you can understand, by intuition. All right, so we have that. Pull out of it. So we get plus 2, then floor function log base 2 of s, the same as our previous a of m plus 1 expression, right? Two sides match the same format. So we have it for the odd case. But next, we need to verify the even case, right? Yeah, we have another half to verify for the even case. All right, so let's continue our proof. Part 2 for even case. When n is even, we use n equals 2s. With s greater or equal to 1, now we make the change, formula transformation, but this time we need to drop that remainder 1 when we do integer division by 2, so we get a of s plus 1. So you will see mathematical induction we can write in this way. So no problem, because the range falls, the range falls into that, right? So we're fine. We can use the mathematical induction assumption. So that's the left-hand side, right? How about the right-hand side? So we want to compare the right-hand side if it takes the same format. Then we're done. So this part a little harder than the previous case. So let's work on it. But this time, 2s plus 1, how do we handle this part? 2s plus 1. There is another nice formula we can use. So this part, if you do not know this formula, then you get stuck. Fortunately, we have it in our textbook, this formula. Okay, this formula. Ceiling function there is a plus 1. Okay, all right, so I give you the reference page you can find in our textbook. All right, so here let us use this formula to make transformation, because we want to have a different representation. So let's do it. But this time, all right, apply this formula, because we want to represent this part, floor function part, right? The floor function part minus 1 to that side. So the floor, this is the n, minus 1 to the other side, right? And use the ceiling function. Okay, so you can see that's the application of this formula. All right, so now we can do simplification. With this, we can do the simplification, because this time 2 common factor, we can take it out, right? Then by logarithm property, we can split. All right, so we can have this plus 1 minus 1, right? Because there is 1 inside that 2, right? That 2, right? Because this equals, if I run one more step, 2 plus s plus 1, right? This equals 1. 1 inside ceiling function bracket, we can pull it out. Pull it out. Okay? So we have this 1 minus 1, so that's why it is gone. All right? It is gone. Then this one, can we apply this formula another time? Because that is the ceiling function. Ceiling function, exactly, we replace n by s. We get this. We get this expression. Okay? Floor function log base 2 of s plus 1. Okay? All right. So that is the floor function of log base 2 of s plus 1, right? Plus this one, right? Yeah. And remember, we need to add that 1. We need to add that 1, right? Add that 1 on top of this expression. Yeah. So at the end, look at the, I hope you can follow. Yeah. At the end, plus 2. Yeah. Because 1 from here, 1 from here. Yeah. So we have 2. You compare these two expressions, exactly the same, right? So that's why we verified n equals even case. Here you can see this step more complicated than the previous case. The reason is we need to use this formula twice. Yeah. And I hope you can follow these two places when we use that special formula. All right, so let me stop our second video here. Yeah. All right.